welcome back. Uh, we were discussing Riemann integration of a function, bounded function, which is mapped from closed interval a b to R. And the way we have defined is that we have defined the upper Riemann sum and lower Riemann sum LPF over a partition P. Then we have defined the infimum of P of UPF. UPF is the upper Riemann sum that we had denoted is that upper integral, and the lower integral to be supremum of P of LPF. So, we say that f is Riemann integrable if these two quantities they agree. If they are equal, then we say that this is Riemann integrable. So, what it is easy to notice that for each partition P, LPF is less or equal to and which is less or equal to a to b upper integral of f, which is less or equal to up of f. Okay, so now how does one test that whether a function is Riemann integrable or not? So there is a criterion of Riemann who says that this is the Riemann criterion. For integrability. It says that if for a given epsilon positive there exists a partition P such that UPF minus of LPF is less than epsilon, then we say that f is going to be, then f is Riemann integrable. That means what we need to show that the upper sum and the lower sum, upper integral and the lower integral, they must be equal, and for every epsilon positive we can find, if we can find a partition which satisfies this condition, then we will say that f is Riemann integrable. Well, I mean the proof is not so it will follow from this inequality. Let us call this as inequality 1. So, from this inequality is true for every partition P. Now, from 1 we get that UPF minus of LPF, this is greater or equal to integral AB f minus BF. So, now we have a partition given any epsilon positive, we have a partition P such that this difference is less than epsilon. Therefore, so for every epsilon integral A B f minus A B f, this is less than epsilon. This will say that integral A B f is less or equal to integral. Thus, and the other side of inequality is always true, therefore, f is Riemann integrable. Riemann integrable. Okay, so this is a nice criterion to judge, I mean, whether a function is Riemann integrable or not. As a matter of fact, this converse is also true if f is Riemann integrable, then for every epsilon positive there exists a partition u p such that u p f minus L p f is less than epsilon. So, now let us get into the prescription of Riemann, which will help us eminently to compute the integral of f, if f is Riemann integrable. Towards that end, let me recall the definition of the limit of a sequence. So, just recall and we will talk about will study convergence of sequence in more details at a later stage. So, just to recall from our class 12 knowledge that let x n be a sequence of real numbers. So, what does that mean? That is for each n belongs to n, we associate a real number called x n. So, you can think of there are in seats like 1, 2, 3, 4, 5, 6 positions, and for each position you are assigning one real number. So, that is what we mean by a sequence. Now, we also know that limit x n goes to infinity is equal to L. That means that eventually this x n will go closer and closer to L as we take n large. So, in other words, we are now familiar with the way we should write this intuitive meaning of x n is close to L for large n, that is for epsilon positive there exists a natural number capital N sub naught belongs to a natural number such that whenever n greater or equal to n sub naught will imply that mod of x n minus of L is less than epsilon. After finitely you fix one epsilon, let it be epsilon to be 0.01. Then you are going to, for this 0.01 you are going to get some n sub naught such that x n minus L is less than 0.01 for all n greater or equal to n sub naught. Similarly, if you take your epsilon 1 by 10 to the power 5, you are going to get a 1 n sub naught. After that, x n minus L is less than 1 by 10 to the power 5. So, after finitely many, you can control the difference between x n and L. So, for example, like let me take x 1 equal to 100, x 2 equal to 75, x 3 equal to 1072, x 4 is equal to 31, x 5 is equal to 1 by 5, x 6 is equal to 1 by 6. In general, x n is equal to 1 by n, n greater or equal to 5. If you are defining, then this sequence, this x n will converge to, so limit of this x n as n goes to infinity, this is going to be 0. because obviously after finitely many leaving out the so whatever changes you are going to make in the first finitely many numbers is not going to affect the convergence of the sequence. Okay, so we will talk more about the sequences, how to test their convergence at a later stage, but this is what we know from class 12. Okay, so coming back to the Riemann condition. So, which is Riemann sum. So, what let P be a partition of A B. That means P is the set of endpoints where A equal to x naught, which is less than x 1 up to x n, which is equal to B. This is the set of x naught x 1 to x n. Now, like this. So, now denote is maximum of mod of x k minus of x k minus of 1. That means, you calculate this distance, this distance, this distance, this whatever. So, given a partition P, so suppose in particular this partition, this I call is as the norm of partition P. This norm P is going to be x 3 minus of x 2 in this particular thing what we are seeing on the screen. So, this is the maximum distance for between two conjugative point, that is what we call as the norm of the partition P. This we call it as partition P. Okay, and let us keep that in mind. So, what Riemann said, as you can see that we have defined the Riemann integral with a partition. So, for UPF we have considered this triangle and this triangle okay. So, and this, and for LPF we have considered the minimum in this interval like this partition, then LPF, UPF, and we go on doing taking the infimum and supremum of the partition. So, what Riemann said is that it really does not matter that what you can do is, if you have some function f, you take the partition and you have the freedom to choose any, this is x naught, x 1, x 2, x 3 dot 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 like this, and this is x n. You can choose C 0, C 1 any point, and you consider the rectangle like this, and here you take any arbitrary point and you consider the rectangle. In here you take any arbitrary point, you get the sum of these rectangles. Now, you take the sum of the area of these rectangles. Now, we keep on make your partition such that x k minus x k minus of 1, they become very small. If you go on doing this process, then what you are going to get is nothing but the integral of f. In other words, what Riemann did is that let us define, let P be a partition A B. Okay. Now, so this P is x naught, x 1, x n, where x naught is equal to A and x n is equal to B. Now, you define S P of f. This is equal to summation k from 1 to n f of C k and then x k minus of x k minus of 1, where C k is any point. You have the freedom to choose any point on the interval x k minus 1 to x k. So, now for a given partition you are going to get n rectangles. Take the sum of the areas of all these rectangles. Now, what Riemann's theorem, what it says is that if limit norm of P goes to 0, S P of f exists. So, for each P you consider S P f, this is called the Riemann sum. And if limit norm P goes to 0, S P f exists, then f is Riemann integrable. And you denote f of x, this to be the Riemann integrable. Well, we are not going to prove this, but this is very useful to compute Riemann integration for a function f, and to check that and how to find the Riemann integration for this. Okay. Now, let us apply this to some known function. Let us say the integral, let us calculate 0 to 1 x dx, which all of us we know. Now, let us compute it with this algorithm, this prescription of Riemann. Let us compute the integration. Okay. So, now 0 to 1, take a partition P of 0 1, call it as x naught to x n. Now, I need to compute S P of f. This is equal to summation over k from 1 to n f of C k, and then this is x k minus of 1. Now, I need to choose this C k between x k minus 1 to x k. Now, choose C k to be x k plus x k minus of 1 by 2. Then definitely this is This is, I am choosing the midpoint x k and x k minus 1 and x k, the midpoint. So, that is in the interval. So, for this particular x k plus x k minus 1 by 2, this choice of C k, what we are going to get? This is, we are going to get that k equal to 1 to n x k plus x k minus of 1 divided by 2 into x k minus of 1. This is equal to half, we can take outside the sum. This summation over k from 1 to n x k plus x k minus 1 into x k minus 1, that is this minus of x k minus of 1 square. So, what is this? This is equal to 1 half k equal to 1 x 1 square minus x 0 square, k equal to 2 plus x 2 square minus x 1 square, x equal to 3 x 3 square minus x 2 square. So, the everything is going to get cancelled except k equal to n and k equal to 1. So, this is x n square minus of x naught square, that is equal to b square minus of a square by 2. Now, what we see is that if you take any partition P, then if you can choose your C k cleverly, what you are going to get is that S p of f is equal to b square minus a square by 2, that is constant. So, now this is the integral, thus this not b square, okay, I can do it as a to b, and then we write this as a to b. So, this is nothing but b square minus a square by 2. So, this, you know, this choice of C k, clever choice of C k is going to be very helpful for us, and we will compute, we will see some more example of by using this Riemann sum. You see, this is where the brilliance of Riemann comes into the picture. So, it is natural to see, as the you are coming from the above initially with the UPF and LPF, you are going from the below, then you say that, I mean, if this matches, then that was Riemann integrable. Then Riemann comes up with that, okay, you have the full freedom of choose any rectangle within the partition that are going to, that is going to do work. Okay, so, one of a easy corollary of that, what we can see is that this is a corollary. Before we get into compute some more example, let us just see this corollary. If f is Riemann integrable on 0 1, then integral of f is equal to limit n goes to infinity 1 by n, then the summation over k is equal to 1 to n f of C k, where C k lies between 1 by k minus of 1 to 1 by k. So, this is because of the theorem what we have proved. Now, you just consider the partition. Oh, this is I am sorry, this is basically k minus of 1 by n to k by n. This is n minus of 1 by n, then n by n, which is equal to 1. So, that is what is the partition. So, you apply now here the b minus of a is 1. So, basically this is what you are going to get with the Riemann integrable. In case of b a to b, you can get the equal distance partition b minus of a by n. So, what it is saying, if you know a priori, if you know that f is Riemann integrable, suppose if somebody told us that okay, f is Riemann integrable, then what we can do is that we can choose our partition to compute the integration, we can choose our partition which are of equal length, because eventually we know that if f is Riemann integrable, then the limit is going to converge. So, therefore, I can make a choice of the partition P, and if that converges to something as n goes past, and you know that a priori because f is Riemann integrable. So, the limit exists. So, this limit whatever I am going to get for this particular case, this is going to be the same. But in order to apply this is very very important that somebody need to tell us that f is Riemann integrable, then we can do this. So, to check whether it is Riemann integrable or not, what we need to do is that we have to find the limit norm p goes to 0 of SPF. Okay, so, let us do few more example. Let us try to get a to b x squared dx. So, now take a partition P, P a partition. Okay. So, now SPF, this is equal to summation over k from 1 to n f of C k, because here f of x is equal to x square, f of C k, then this is x k minus of x k minus of 1. So, I choose my C k to be x k square plus x k plus x k minus of 1 divided by 3 whole to the power 1 by 2. As you can see that x k minus of 1 square is lesser equal to C k square, because x k minus of 1 square is lesser equal to x k square. X k is lying on the right hand side of x k minus of 1, x k into x k minus this one is greater or equal to x k minus 1 square, and x k minus of 1 square is this. Now, this is 3 times you divided it by 3. So, this and this is similar argument, this is lesser equal to x k square. So, C k is lying between x k minus of 1 to x k. So, now we have right choice of C k. Therefore, as for this choice of C k, what we are going to get 1 by 3 is going to come out of it, and we have x k square plus x k minus of 1 plus x k minus of 1 square into x k minus of 1. This is equal to 1 by 3 summation over k equal to 1 to n x k cube minus of x k minus of 1 cube. Now, this is a telescopic sum in the sense that k equal to 1 x 1 cube minus x naught cube plus x 2 cube minus x 1 cube. So, everything in between is going to get cancelled, and k equal to n x n cube minus x n minus of 1 cube. So, this is 1 by 3 x n cube minus of x naught cube, that is what is the remaining term. So, this is 1 by 3 b q minus of a q. Therefore, the limit SPF for any p by a clever choice of C k, this is going to be constant. Therefore, it does not matter what partition you take. Now, if you take the limit, this is going to be 1 by 3 b q minus of a q. So, as per Riemann, this integral is nothing but b q minus of a q by 3. So, this is a very nice prescription to compute Riemann integration with the prescription of Riemann. We will continue doing some few more example and see that what are some large class of function which are Riemann integrable. So, thank you.